Hello, my name is Tom Klepper, and welcome to the first part of the Basic Electrical Circuits class. This is taught at the Route 9 Library and Innovation Center in Wilmington, Delaware. So this is part one. We're going to go over current, resistance, and voltage. Essentially, you're going to learn what electricity is today. So we're going to go over materials, which are conductors and insulators, briefly. Then move on to electrical current, which is charges that move through wires. Then we're talking about resistance inside the wire and something called a resistor. And finally wrap up with voltage using the waterfall analogy that a lot of folks like to use. So in materials, atoms are the basic building block of all materials. An atom has a nucleus in the center, electrons that go around it, very much like our solar system has a sun in the center and the planets that orbit around. And you could almost think there are things called free electrons, which are like free planets, maybe more like comets, that can come into the solar system and leave the solar system. These are going to be the key parts of electricity, are these electrons that are shared. So inside of a metal, the atoms are arranged in this kind of lattice structure. So each one of these balls would be an atom with these electrons tightly bound to the center, and there would be a lot of free electrons that can roam from one atom to the other interspersed in metals. However, in insulators, they're still made up of atoms, but they're in these long molecular chains, and they don't have free electrons that can move in between them. So the takeaway from this slide is essentially this. In metals that are made up of atoms within this lattice structure, they do have free electrons that can move about them, but in insulators there are no free electrons. So metals make very good conductors of these electrons, and insulators do not. So when we don't want to look at these free or shared electrons inside of metals, let's form a piece of metal into a wire cylinder. So here's a graphic I had done a number of years ago that shows a wire, cylindrical wire, and we're going to peek inside when there's no current flowing. Oops, let's go back. Here we go. So if you can look at that, the blue dots represent the atoms in this lattice structure. They're kind of fixed. The red dots represent the free electrons that can move easily from one atom to the other. If you notice that the electrons move kind of randomly around from one side to the other, there's no net flow of electrons. They just kind of moving randomly amongst the atoms. However, if we were to apply a force, let's say a battery, we connect from one side of the wire to the other, and we peek inside, what we'll notice is the electrons are still moving about from one atom to the other, but there's a general net flow of electrons from one side to the other. And this is actual electrical current flowing. It's the movement of these electrons from one side of the wire to the other as they move about amongst the atoms. That is electrical current flow. It is kind of interesting to note that there are these things called free electrons, right? And they do move about the atoms, but they're still tightly bound to that lattice of atoms. They can't leave the metal, for instance. They are very tightly bound inside of there. So here's a kind of analogy that I like to use. It's a little simpler. So let's say you have people going to a concert, and they're going to go into this auditorium, and there's lots of people out here in the lobby waiting to get into a very long, narrow hallway. So right now the auditorium doors are closed, and people in there, they're milling about, they're talking, they're moving to the left, they're moving to the right, there's a whole bunch of them, but there's no net movement of people down the hallway. If we all of a sudden open the doors to the auditorium, then you're going to start seeing people move through the hallway, right? They may move still around talking, etc., but there will be a net movement of people. And it's interesting to note that if you go back to the point where the doors were closed, the minute you open a door, people are going to start coming out, like instantly. You're going to come out into the auditorium, and people will be going into the lobby. But a particular person, if you track them, will take time to muddle about to get down this hallway to there. So if you wanted to look at how long did it take for people to go into the auditorium, it's instantaneous. As soon as you open the door, people go in. However, if you track a particular person, it may take longer for that person to get down the hallway. It's very similar in electrons in wires. The direction of flow in this situation, we're going from right to left. And if you were to kind of set up a boundary here, so right through the cross section of the hallway, and let's say you have an attendant here, and they're going to count the number of people per time interval, let's say per second. So he's got a little stop or clicker there, and he's counting the time people, the number of people that pass through this part in time. And maybe he's collecting money. So maybe every time somebody goes through, they pay a $10 entrance fee. He could actually collect the total amount of money per second that you're going to collect for this concert. So it's very similar to current flow. So he's not only counting the number of people, but he's counting the total money per second that you would get as these people flow through this particular arbitrary boundary here. So with those two kind of analogies, let's just look at the definition of current. Now, here's the formula. We will never have to do this calculation, but I just wanted to show you that current, electrical current, is literally the total charge flowing through the cross section of the wire within, let's say, 1 second or some interval of time. And again, the total charge is similar to what we did before. It's the number of electrons times the charge of each electron, just like we had the number of people times, let's say, the entrance fee per. So this is the definition of electrical current. It's no more complicated. It's very simple. And just wanted to show with this formula, that's where it comes from. It's literally the electron flowing through a wire. So let's take another look at the electron. And I mentioned before that when you first open the doors to the hallway, that people start going through instantly. So the effect of the movement is instantaneous, although if you track a particular person, it takes a while. So I'm going to simulate electron movement down a wire using these magnets on a rod. So if you look at this little graphic, you can see that the effect, as I pulse the magnets, the effect goes really quickly. But if you look at the travel of each individual magnet, it takes a while to traverse down the wire. So this is very similar to electrons. So the minute you induce electrons to flow down the wire, the effect is instantaneous. But if you were to track a particular electron as it scoots down the wire, it's much slower. So as a matter of fact, how fast do electrons move? Well, the velocity or group velocity of them is at the speed of light. So literally the effect of when you first turn it on of the electrons moving down the wire happens at the speed of light, meaning that when you turn on the electrical switch at your wall, your light turns on essentially about at the speed of light later, very quickly. But if you were to track a particular electron as it meanders down the line, it's only about a millimeter a second. They call that the drift velocity. So kind of an interesting little fun fact about how electrons move down wires. Now we're going to move on to the concept of resistance. So if we go back to our analogy of the hallway, people are moving down the hallway, and all of a sudden I throw in a partition, like a wall or an obstacle right there. You can imagine that what's going to happen is as soon as I put that partition in, you're going to get kind of a buildup of people on this side, and the number of people that are going to go through are slower because they kind of eke around each side of the partition. So if you go back to our guy looking at this kind of arbitrary cross section, he's going to count less number of people per second going through, and of course the total money per second is going to be less. So we put a resistance or this kind of obstacle in here, and this is a decent analogy to what resistance to current flow is. So in wires, we don't have to figure out the mechanism exactly of what's causing this resistance of electrons to flow down it. The nice thing is there's a parameter. It's called resistivity. It's an intrinsic property of the metals that specifies how easily electrons flow down the wire. And you could look it up in this table. It's resistivity. It's got the units of nano ohm meters. If you go back to our SI list, nano is basically 1/1000th of an ohm meter. Very, very tiny. So in this table, the lower the number, the easier it is for electrons to flow down the wire. The bigger the number, the harder it is. So essentially, the lower this number, the lower the resistance that wire will have to electrons flowing down it, and the bigger the number, the harder or higher resistance it's going to have for electrons flowing down the wire. And as a kind of a side note, generally as temperature increases, this value, this intrinsic value will increase as well. So you notice this table was written down at room temperature. As temperature increases, these values will increase slightly. As it decreases from room temperature, they'll decrease slightly, just kind of as a fun fact there. So again, we don't need to know exactly what causes the electrons to flow slower down one metal versus another. Not slower, but less density. But this table, you can just look it up and it'll give you the intrinsic values. So let's calculate the resistance of a wire. So ultimately, this is kind of what we've been building to in the last few slides, because we're saying we have metal conductors that we're going to draw into a cylinder. They make a wire, and electrons will flow down the wire. That makes up current. So we know what current is. We know that there's some resistance to that current in this wire, and we can figure out what that resistance is using these formulas. So essentially, we're going to have a cross section to the wire. So you need to know that what the area of the cross section of a wire. If it's a cylindrical wire, it'd be pi r squared. You need to know the length of the wire, and then using this formula, we can figure out the total resistance, which is the restriction of electron flow down the wire, is equal to this resistivity value that you look up in a table times the length of the wire divided by the cross section of the wire. We also learned in our intro that if the cross section is given in, let's say, inches squared, and we need it in millimeters squared, we know how to convert that. So let's just take a look at this little table here and ask the question. If we take the area, the cross-sectional area of this wire, and we increase the cross-sectional area, the resistance will decrease. And you can see that right from the formula. If I take A and I make A bigger, the denominator is bigger, which means this whole factor gets less, or R gets less. If we take the length of the wire here and we increase the length of the wire, the resistance should increase. And we can see that here because the numerator increases in L, which is directly proportional to R. And then again, that side note, if you take temperature and increase it, the overall resistance will increase as well. So this gives you an idea of if you needed to calculate the resistance of a wire, you could use this formula. And it also kind of gives you an idea of what impacts resistance. So obviously, if I have a wire, and I have a thicker wire, if you will, it's going to have lower resistance. If I have a shorter wire, it will have lower resistance as well. So there's things called American wire gauge, and these are standard sizes for wires. So as it turns out, the bigger the number it is for the gauge, the smaller the diameter for whatever reason, and then the lower number, the bigger it is. So typical values are 18 gauge to 40 gauge. Typical house wiring might be a 12 gauge wire is house wiring. The projects that we do, I think, are going to be something like 22 gauge. So that'll be in this range. And you'll see that some of these have solid or make up of solid cylinders, and some are made up of bunches of solid. They call this stranded wire. And essentially the only difference, the only reason that we have stranded wires is that it makes it easier to bend and more flexible. So it's almost like this stranded wire is just made up of a bunch of these solid wires, essentially what it is. So it's not really for electrical reasons they do this. It's mostly for mechanical and bendability, routability reasons. And you could look up in the table. Here's the American wire gauge size. You can go over here and look at here's the effective diameter of it. These are obviously for very big wires. Here's the diameter in inches, diameter in millimeters, and here's the area in millimeters, and then here's the resistance for feet. So you don't even have to do the calculation we had. You can just look it up in this table. But suffice it to say, you can look up for a 12 gauge wire. It's about 1.5 or 1.6 ohms per 1,000 feet. Not a lot. It's actually very, very little. Which is one of the reasons why when we wire up our circuits, for the most part, we're not going to worry about the resistance of a wire. There are some examples, and we're going to go over one later, where you do really care about the resistance of a wire. So next we're going to talk about something called a resistor. This is like an intentional resistance, and you're going to see in our examples when we talk about circuits, there are going to be times where you're going to want to put in an intentional resistance or resistor for the purpose of limiting the current flow. So kind of going back to what the definition of current is, there are times where you want to restrict that current flow through your circuit, and you're going to do that using a resistor. So these are very cheap devices. They're sub pennies a piece, and they're their value is decided by using this color coding. So here's a bunch of resistors, and essentially the color coding works like this. In these scenarios, there's a gold or a silver band that talks about the tolerance. That's how precise it is. So a 5% gold means that it's a little bit more tighter tolerance than the 10% silver. So in this situation, you go on the opposite side of the gold and you look at the color. So this one's orange, which is a 3, the first digit. The next one is a white, which is a 9. And then the third one is the multiplier, which is an orange, which is 1,000. So this resistance is 39,000 ohms, or if we use our SI units, it's 39 kilo ohms. We go to the next one. We say yellow is a 4, purple is a 7, and a black is a multiplier of 1. So that's 47 ohms. The next one would be a brown, which is a 1, a green, which is a 5, and a red multiplier of 100. So that's 1, 5 times 100. It's 15 times 100, or 1,500 ohms, or 1.5 kilo ohms. Here we have brown, black, brown. That's 1, 0, and brown is a multiplier times 10. So that's essentially 10, 1, 0 times 10, or 100. This one is a 2 and a 2 with a multiplier of 100. So that's literally 22 times 100, or 2,200 ohms, or 2.2 kilo ohms. And then finally we have a 4, a 7 with a orange, which is 1,000, 47,000 ohms, or 47 kilo ohms. So this shows you how, when you get a bag of resistors, you can pick out the value that you want. And we'll go over more when we talk about Ohm's law, about how you select a resistor, why we just select a resistor. But I just wanted to say that yes, there are these things called resistors, are used intentionally to reduce the current flow, and you'll notice that you will get a voltage drop, which we'll discuss next. So let's get into voltage. So we're going to talk about voltage using this very simple circuit. So when I say voltage source, in this case we're using a battery. A voltage has the potential to do work if you connect it to a completed circuit. So what that means, if you look at this little circuit, we have a voltage source, a battery, and these wires, which for right now we're going to assume have no resistance to them, and it's connected to a light bulb, but the switch is open. So when the switch is open, no current can flow. This is very similar to our analogy with the auditorium and the hallway. When the doors of the auditorium are closed, people are milling about in there, but no flow is happening. People are not moving into the auditorium. Same thing here. The electrons are in the battery, they're in the wire, they're sitting there, there's just no current flow is happening. The minute we close the switch and we complete the circuit, so the wires, the metal are connected all the way through our circuit, we get current flow, and of course the light bulb will light. This is analogous to somebody opening up the doors to our hallway and people flowing into the auditorium. So every battery, every voltage source will have a positive and negative. This is just by convention. In this case, the D-cell battery, the little cap on top is the positive, and the wider one, metallic thing on the bottom one, is negative. When you connect this through, and you might want to ask, well, where's the direction of flow of the electrons? Because we know now that the electrons are the ones doing the work. They're going from minus through all the way to positive. That is the flow, the direction the electrons are flowing through the circuit. Okay. However, Benjamin Franklin, when he first talked about electricity, defined a current flow in the opposite. We now call this conventional current flow, and he goes from positive to negative. As it turns out, it doesn't matter which convention or direction you pick, as long as you're consistent. When we get into Ohm's law, you can pick either direction and the math will work out correctly. But from now on, just for sake of convention, when we talk about current flow, we're always going to go from positive to negative, even though we know in the back of our mind the electrons are moving from negative to positive. So this is our simple circuit, kind of as a recap. We got a battery, positive and negative, our conventional currents flowing through the circuit, and that's, so we've talked about the current flow. We've talked about of course resistance. In this case, our light bulb has a lot of resistance, and we've talked about a voltage source which has the potential to do work. So let's look at this voltage source a little bit more. this battery really only has the ability to do work if I consider both electrodes, right? If I cut this battery in half and I just look at this piece of metal alone, there's no voltage. It always has to be in reference to something. You have to say, oh, this piece of metal right here has a voltage reference to the bottom part of it. You can't have one without the other. Voltage only has the potential to work if you have both terminals. Let me give you an interesting analogy to this. Let's look at the Hoover Dam, which we know has the potential to do work. So Lake Mead, which is what feeds the Hoover Dam, here's a picture of Lake Mead, right? And if I said, we're sitting right here and I say, hey, Lake Mead is this high. It doesn't mean anything. Here's the surface of Lake Mead right there. But it means nothing unless it's reference to the height of the Hoover Dam. When you look at it this way, you go, oh, I see, that has a lot of potential to do work. It generates a lot of electricity. So in this analogy, you have to not just look at the height of it in terms of right there, it needs to be referenced to something like the Hoover Dam. So let's tie voltage, current, resistance together using the water analogy, which is, in some respects, the one that most people use. So we're going to say that voltage is equal to the height of the water column. Again, we know that if you take, let's say you take a 1 foot diameter, pipe, and I fill it full of 5 feet of water and I drill a 1-inch hole in the bottom, I can probably stop the water from flowing with my hand. But if I make that 1 foot pipe the height of the Hoover Dam, the pressure that goes down is going to be so great I won't be able to stop that. So essentially the height of the water here in our analogy references the pressure of the water coming out of the hole. So essentially this voltage is reference to pressure in water. The current, however, is reference to the flow, and we've talked about current being a flow. So the water flowing through the hole is analogous to the current of the amperage. So if you have a larger hole here, more water is going to flow out than if you had a tiny one. And you can think about the water flow as this aperture filling a bucket full of water, and you might ask how quickly can that bucket of water be filled up if this aperture is bigger versus smaller. And you can know intuitively that if you had a hose with a small diameter, it's going to take a lot longer to fill up the bucket than if you had a big, a larger diameter hose. So that's the flow and then resistance in terms of water flow is, again, you go back to your garden hose and the water is flowing through it. If I squeeze the garden hose, I'm going to create a resistance. You're going to have less water coming out of the garden hose. We know that. And we also know that we're kind of building up pressure on this side of the resistance. So essentially, when we apply a resistance in this situation where we have a voltage source that's creating the pressure in the first place, we have flow going through this garden hose. The minute I squeeze the garden hose, there will be a pressure drop. The pressure on this side will be higher than the pressure on this. That pressure drop is like a voltage drop, because remember I said pressure is analogous to voltage here. So we can look at a circuit the same way. If I have a water pump and it's pumping water through a closed loop, and I squeeze it right there, I'm going to get a resistance. The pressure on this side is going to be higher than the pressure on this side due to that resistance. It's kind of an intuitive thing. You can also do this if you think about an HVAC system or any system that's closed loop and there's a fluid flowing through. When we go to our electrical system, we have our power supply or battery, we have our conventional current flowing through it, and we have a resistance. Here we have a higher potential, and there we have the lower potential. And just like the water analogy, we're going to have a voltage drop across this resistor. It's going to be higher here than there because essentially we're reducing the amount of current flowing through here. You have literally a buildup of density of electrons here. So the higher density of electrons, the higher pressure, compared, again, reference to here, means there will be a voltage drop across that. And this essentially builds the foundational understanding for Ohm's law, where we've talked about voltage, current, and resistance, and how they might work together in a circuit, which is what we're going to talk about in the next part. So this kind of ends this first part where we introduce current, resistance, and voltage. And then in class on Tuesday, I'm going to go over how you pull it all together with Ohm's law and power and how they're all tied together. So thanks for listening, and we'll see you on Tuesday.